Gauss's law tells us that the electric flux, phi sub E, through a closed surface is proportional to the charge Q enclosed by that surface. In this equation, epsilon sub 0 is a constant known as the permittivity of free space. Before we explore Gauss's law further, it would be a good idea to discuss the concept of electric flux. In this equation for electric flux, phi sub E is equal to the summation of the magnitude E of the electric field times the cosine of the angle phi, all multiplied by the area, delta A, of a small section of the Gaussian surface. Conceptually, we have an arbitrary surface through which an electric field is passing. We are taking that surface and breaking it into small pieces. For each small piece of surface, phi is the angle between the direction of the electric field and the normal to the surface. In Gauss's law, the closed surface may be any arbitrary shape. However, this can be difficult to deal with mathematically. It is very helpful to choose a surface that matches the symmetry of the charge distribution you are analyzing. Let's examine the equation for electric flux for a simple Gaussian surface, and then use Gauss's law to find an expression for the magnitude of the electric field produced by the charge distribution contained within the closed surface. We will examine the case of a solid spherical conducting shell with excess positive charge Q. We will choose a spherical surface centered on the shell and a distance r from the center of the shell. If we imagine the normal to our surface, or Gaussian surface, we will see that for every small section of the surface, the electric field is pointing in the same direction as the normal to the surface. Therefore, in our equation for electric flux, the angle phi is equal to 0 degrees. In the case of a spherical charge distribution, choosing a spherical Gaussian surface means each small piece of the Gaussian surface has the same electric field going perpendicularly to the surface. So the summation of the magnitude of the electric field times the areas of all the pieces is just equal to the E times the total surface area A of the sphere. The electric flux will then be equal to the magnitude E of the electric field times A, the area of the Gaussian surface. For a spherical surface, the area is equal to 4 times pi times r squared, where r is the radius of the sphere. Gauss's law will now allow us to find an expression for the magnitude of the electric field at the Gaussian surface, which is a sphere a distance of little r away from the center. The law says that the electric flux is equal to the enclosed charged Q divided by the constant epsilon sub 0. When we specify the area for this situation, we obtain an expression for the electric flux, which is an important part of Gauss's law. If we now bring in Gauss's law, we can find an expression for the value of the electric field's magnitude. Combining the equations for electric flux and solving for the magnitude of the electric field, we find that it is equal to the total enclosed charge divided by the quantity of 4 times pi times epsilon sub 0 times r squared. If we think about it, this makes sense because outside of the spherical shell, the charge distribution looks like a point charge. The result we just obtained backs this up. If you remember that K is defined as 1 divided by the quantity of 4 times pi times epsilon sub 0, we are right back at equation 18.3.